Hi guys, welcome. So I've taken some of the feedback from the students. They've been complaining that I stream way too late, before a day before the exam is way too late. So I'm just gonna start streaming now. So just breaking down the topics into three topics. So if those few people in the chat, if you can let me know that you can hear me okay, that'll be fantastic. Then we'll make a start. So what I'll do is essentially just go through, as you can see on the screen, a 2016 exam paper. I'll just speed run this particular paper, just go through all the key points. Just make sure that I think the best way to cover the key concept is just go through some of the questions. Okay, so this is 2016. I haven't done this before on my YouTube channel, so maybe you haven't done this particular exam, so that's okay. So we're just gonna make a start. All right, so if you think about this particular topic, this topic breaks down into three big sections. Okay, three questions. The first question is, well, the first concept that I normally start teaching is Lewis structures and shapes of molecules and polarity. Okay, so that's normally the big first question. The second question is looking at types of solids. Okay, so you got molecular solids, giant covalent network, ionic solid, and what's the other one that I forgot? Metallic, ionic, giant covalent network, and molecular. Okay, so those are 4 types of solids. And then the third question looks at enthalpy, which you need to do some calculations. Okay, so we're just gonna use this as an example. So I'm just gonna start with the Lewis diagrams. So here we are. So the question is a little bit different. Like the order of the question is a little bit different. Okay, so we're just gonna try this one. Let's just make sure my pen works. So here we go, water. Now to draw the Lewis structure. So if you have seen my YouTube channel, if you have seen my videos before, you know how to draw this by now, hopefully. My way of doing this is just, if you really struggle, I mean, you've done organics by now, you know that hydrogen bond once and oxygen bond twice, and this is your Lewis diagram for this. Okay, and if you guys have questions about anything in this particular topic, then just chuck in the comment section. I see, yeah, level 2 physics was today. Hopefully that wasn't too bad. I talked to a couple of people and they said it was okay. So maybe chem wouldn't be too bad for you. All right, so that's H2O. This is bent. So this has got 1, 2, 3, 4 regions of electron density around the central oxygen atom, and that's why it has a tetrahedral arrangement, because you got 4 things around it, but only 2 of them are involved in bonding. We have this particular type of arrangement. This is a bent shape, and they told you it's 109.5 degrees. Now something that you could remember, guys, is that whenever you have 4 regions of electron density around your central atom, everything has a, you can tell here, if you got 4 regions of electron density, the bond angle is always going to be 109.5 degrees. Okay, it's not always going to be 109.5 degrees. The more chemistry you learn later on, the more you understand that the bond angle differ a little bit. Okay, is the name of the shape established through the number of electron pairs. Yes, so you look at the so for H2O, so just gonna highlight this: 1, 2, 3, 4 regions. 2 are bonded, 2 are not, 2 are lone pairs. So this is a tetrahedral, this is a tetrahedral arrangement, but you can only see 2 of the corners, hence it's bent. Okay, you can look at pH3 as an example. pH3 look like this. So again, this is you're looking at 1, 2, 3, 4 regions of electron density. That's why the bond angle is 109.5, because you got 4 things pushing each other away. So the bond angle is always going to be 109.5 degrees. Okay. Now for CS2 is a little bit different. Now if you don't know how to do CS2, you can use my method over here. I mean, not my method, but that's how I've been taught and how I tend to teach others how I do this. So you look at carbon, you look at how many valence electrons they have. So carbon has 4 valence electrons, sulfur has 6, sulfur has 6. They need 8, they need 8, they need 8. So they need 24. You have 24 electrons and they have 16. So you have 16 electrons, but you need 24. 24 minus 16 equals 8. So that means this is 8 bonding electrons. That means you have 4 bonds, 4 lines. So put your carbon in the middle, 4 lines, 1, 2, 3, 4. But now all of you guys have done organic. You should know that the carbon always bonds 4 times. So that's why it has 4 bonds around it. But this is a, that's why I always tell my year 12s that chemistry get progressively easier the more you do, because it just makes more sense. Okay, so if you look at CS2, let's look at the central carbon atom. We got 1, 2 density, 2 densities. That's why it's 180 degrees. So this has a linear shape, and this has a trigonal pyramid shape. Excuse me, my neighbors is lighting up fireworks, even though it's way after guy folks, but who cares about the laws nowadays, eh? So compare and contrast the shape. So you can look at the answers. Again, I'm not going to go through this in too much detail, because you can have a look at the answers. Okay, but if you want to compare the shapes and bond angles in this particular question, you just talk about how many regions of electron density are there around the central atom, how many of them are bonded, how many of them you can actually see, and therefore that will determine the shape. Okay. When's the next one? Stacy, if you look at my my post that I chucked earlier, so I have like a 3-day rotation. So it's organic, it's structure. So it's year 12 today, year 11 tomorrow, year 13 the day after, and then it's year 12 again. So just one topic a day for a different year level, so you can have a look up on the stream. I think it's 4 days later. Okay, so not tomorrow, so it's going to be Thursday organic. Okay, all right. So that's a Lewis structure. Now next one is, it's on my YouTube channel. Okay. The Lewis structure, I mean, to be honest, organic is probably the one that can help the least through the screen, because it's very, very unpredictable. Okay, whereas structure bonding is so predictable. That's why there's not many people here, which is a good thing. That means you guys understood this. Now let's have a look at this. The Lewis structure for this. So this has a trigonal pyramid shape. Which is asymmetrical, and if you look at Borane, this is trigonal planar, which is symmetrical. Okay, now they want you to talk about why NH3 is polar and BH3 is non-polar. So it's very straightforward. But one key thing that you need to talk about, so you can do it like this. You can talk about NH3, but you need to say that the bonding, so the key thing that you always, I get so tired of people not doing this, even people from my own class, despite how many times I tell them to do this. You need to talk about the bonding. You know how a lot of, you're probably sitting here listening and go, all right, the bond dipole cancel or don't cancel, therefore, say symmetrical, cancels, don't cancel, polar, non-polar, da-di-da-di-da. But if you don't tell us where the dipoles come from, then your discussion is incomplete, because you're talking about bond dipoles canceling each other out, but where the heck did the bond dipoles come from? Okay, so for example, with NH, you need to tell us that this bond is polar due to significant electronegativity difference, which give us bond dipoles. Okay, so we have bond dipoles as a result. And then we have got this particular structure, which is trigonal pyramid. So the shape is asymmetrical. Therefore the dipoles will remain. They don't cancel out. Therefore it's polar. Okay. So whereas the other one, when you look at BH3, again, don't be lazy. Just write it like this. First, you always talk about BH bond. Okay, so this bond is polar. Why is that? Because of the significant electronegativity difference between B and H. You don't need to tell us which one is You don't need to tell us which one is more electronegative, but you just need to tell us that the difference is significant enough. Okay, so this is polar, and therefore the shape is symmetrical, and therefore, you know, the polar dipoles, you got bond dipoles, but because you have symmetrical shape, therefore it cancels out, and this is not polar. And someone in the chat asked me which shape is symmetrical. So this is kind of like which shape is symmetrical. So your linear, your trigonal planar, and your tetrahedral. So these are your symmetrical shapes. Okay, but the key thing that you must remember, like say for example, I can have CH, CH, CL, CL. This is tetrahedral, but this shape is kind of symmetrical. But then the bond dipoles don't cancel out because you got CH, you got CCl, you got two different strength of bond dipoles. So it's almost like you got, you know, they don't cancel out, even though on the diagram it looks like it does, but it's not. Okay, so that's just, you know, you've done this enough at this stage of the year. If you still unfamiliar with this, and you know, good luck to learn this in a week. So that's pretty much the first chunk. Okay, so if you scroll down, yeah, that's just enthalpy. The second chunk that I talked about is going to be on solids. So you can see here, you always see a table like this in the exam, which is very, very standard. So if you see zinc Cl2, so, and people always go, how do you know what type of solid it is? So remember, when you see graphite, you know, silicon dioxide, so these are all giant covalent network, and these are made of carbon atoms, and obviously made of covalent bonding. Okay, so you can identify those quite easily. And then you have, you know, things like zinc chloride and CO2. So this is where you need to actually look at the composition of the thing that we're dealing with. So if you look at ZnCl2, so the Zn is a metal, and then the Cl is a non-metal, whereas carbon is a non-metal and oxygen is a non-metal. So, you know, you got two different types of substance here. When you got metal, non-metal, this is ionic. When you have non-metal, this is molecular. Okay, so that's how you can remember. And type of atoms, type of particles, ions, type of particles, molecule, and then attractive force between particles. This is ionic bonding. And CO2, this is just weak intermolecular forces, or van der Waals attraction, whichever one you want to remember. Okay. Just come right on this. If you guys worry about organic, come on. I mean, it literally is like a 2-hour job. If you just put your phone away, don't print it out, don't look at your screen, and you should be able to remember it. So maybe come on the 10th, I'll show you how you can, you know, put everything together. Organics, it's 10th of November. All right. Now next one. So just on the community chat, there is a link to, like, you know, all the stream schedules. Right. Next one. And then the next bit is looking at the physical properties. Okay, so the physical properties are these followings. So again, I'm speed running this paper, but these are the things you need to look at: melting point / boiling point. And then you got electrical conductivity, and you got solubility. And then you have got malleability. Okay, so these are your four main four main properties that you need to be able to compare, and that just comes down to literally just practicing and just seeing all the variations. If you've done 3-4 years of exam papers, you will know exactly what I mean. It's the same bloody questions. They just change the wording, change the solids, but the questions are still the same. Okay, so this one's conductivity. So they say it's conducts electricity when solid, whereas zinc chloride will not conduct electricity solid when it's molten. So this is where you just need to understand graphite is when you have a layer and then another layer, then another layer of carbon atoms, and in between you have those lone pairs of electrons between those two-dimensional layers, which are free moving, which will conduct electricity. Okay, and then you got zinc chloride. So you got zinc chloride, which is a positive bonding to a negative, bonding to a negative, those negative bonding to a positive, something like that. And then the negative bonding to a positive, positive bonding to a negative, negative bonding to the positive, It's the same, something like that, three-dimensional letters. But what happens, that's why in a solid structure, they do not conduct electricity, because those ions are not free moving. They cannot move around easily, therefore they can't conduct electricity. Whereas once it's molten, that means these positive and negative ions become free moving and they can carry charges. Okay, so it's just a lot of grinding, guys. There's no other way to it. I've always said chem is so fair, like especially level 2. You spend the hours, you will get good grades. Okay, next one, let's look at this. This is solubility. Okay, solubility, just fine in terms of blah 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 blah. Okay, so zinc, again, this is ionic solid. Now and then CO2, this is molecular. Now CO2 is a non-polar molecule, whereas water is a polar solvent. Now please guys, if you are listening to this and if you don't know how to talk about solubility, please don't just say like dissolves like and expect us to give you the grade. You won't get much out of it. You're probably getting achieved if you're lucky. Okay, because that's not an explanation. Like dissolves like. So what the heck does that actually mean? So you need to understand, for something to dissolve, for anything to dissolve in a solvent, that's because the force of attraction between the I'm just checking. The force of attraction between the solvent, like say for example, before you have the solute, you have the solvent. Okay, so the solute are the things you're trying to dissolve, solvent is the thing that you're dissolving it in, and then you mix them together, they dissolve, and then you have a solution. Okay, so why does that dissolve? Why does it dissolve? It's because the force of attraction between the solute and the force of attraction between the solvent is not that strong. So when these guys meet together, the force of attraction between the solute and the solvent is stronger than what you had before individually, just in the things you're trying to dissolve and in the solvent themselves. So when you mix them together, the combination, the new combination, the new force of attraction is stronger than what you had before. Therefore they dissolve. If they don't dissolve, that means the force of attraction that you have currently, solute and solute, solvent, solvent, is stronger than what it could have been if they dissolved. So they just don't do it. They're happy with their with each other as it is. So with zinc chloride, for example, your zinc gets pulled apart, so your water do this. Your water has positive and negative ends. So what happens with the zinc is that your negative end, the oxygen, which is a negative end, will surround the Zn2+, and then the positive end from the water will surround the Cr-. So this force of attraction is stronger. This is stronger than zinc and Cl and water and water. Okay, so this is stronger. That's why it dissolves. So why doesn't CO2 dissolve in water? So if you have CO2, you mix it in water, why does that not dissolve? No dissolving. Why doesn't that dissolve? You can talk about the polarity here. You can talk about this being polar. You can talk about this being non-polar. Okay, so what it means is that you got these polar molecules. You got this water, the water hanging out with each other. you know, positive end, negative ends. You'd learn more of this in year 13. This is, you know, this is intermolecular force. They got polar bonds, they got dipoles, and they got positive ends, negative ends, and they can, you know, interact with each other quite easily. So this force of attraction, so if you think about it, these guys, these water molecules, are very happy with each other. The force of attraction between those two water molecules is stronger than what they could have achieved with CO2. Because CO2 is really boring. It's non-polar. It's no charge. It has no poles. It has nothing that the water likes. So they just been like, we're just gonna hang out with our mates, and you're trying to blend in. Nope, sorry. Okay, you can go hang out with the other friends. Okay, so that's why it doesn't dissolve. Right, so do you have to mention solute, solvent, or can we just like, so Stacey, for the explanation, yep, you just need to say, you know, you don't, the solute and solvent is more of a general, you know, example. So it could be any solvent, could be any solute. I'm just giving you, but you do want to be more specific. All right, so that's your solids parts, and then the next big chunk is enthalpy. Okay, so as you can see, again, I'm just using this paper just to go through some of the important concepts. I believe most people, you know, that's currently on the live streams do recognize quite a few of those names. You probably have seen quite a few of my videos, and yeah, and apologies with some of the mistakes that I do make them, because I make them like towards midnight, and you know, quite tiring. But let's have a look at this. Blah 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 blah. You know, wonder packs activate. Wait, King Gamer, what did you just say? Your statement. What statement? What statement did you make? Send it again. So the salt dissolves in water, causing the temperature to decrease. Temperature to decrease. Temperature to decrease. Okay, so you put it on to someone and it cools them down. So that means it's you are, when the salt dissolves in water, causing the temperature to decrease, and that means it's sucking energy away from you. So this is endothermic. Okay, because if the exothermic is hotter, endothermic means it's cooler. And why is that? Because temperature decreases. Next one for so I don't even read this, I just look at that. If the delta H is negative, so it's exothermic, and explain why, because the number is negative. Done. Okay. Next one, pentane is a liquid at room temperature. So you just need to understand the basics. Indo, exo. Indo is when you have something like this. Exo is when you have something like this. This is the change of enthalpy. This is your reactants. This is your products. And then this is your activation energy. And you know, this is your change of enthalpy. This change in enthalpy is positive, this is negative, this is exo, this is indo. Okay, all right, so they said the pentane is a room, evaporates at 31 degrees, which is an endothermic. Why the evaporation is endothermic? Endothermic because it's bonds breaking. You need to, or force breaking, we normally say endothermic is bonds breaking, because you, if you're trying to, so you got pentane, like I said, this is a molecule pentane, this is a molecule pentane, this is a molecule pentane, molecule pentane, molecule pentane, pentane. And what's going to happen, like how do you turn this into, you know, if you turn to gas, what does that mean? That means you separate the molecules. You are breaking the intermolecular forces between these molecules, so that means you need to give it energy. They're not going to do it naturally by themselves. You need to give them energy, and once they absorb the energy, they break those intermolecular forces in this particular example, and then they go away, become gases. Okay. Quick question about write-up for property type. Do we always write 3D letters within the write-up? Yes, please do that. We look at the surrounding temperature, right, for exo, indo. Yep. Enthalpy is always exo. Negative enthalpy is obviously exo. Yep. Endothermic means bonds are breaking. Yep. Yep. You're right. Kingmaker. King Gamer. Sorry. So you got endothermic always breaking bonds, and exothermic is making bonds. Like you can just remember one, and the other one's the opposite. So go with the one that makes the most sense. So if you are absorbing heat, it will break the existing bonds. Endothermic. Okay. All right, and try to focus on one. Good E to pass. Yeah, it's structure and bonding. It's so easy to pass, and I'm not saying it just because I'm a teacher. You know, it's so easy to pass. You literally, like, seriously, look at the past 5 years of structure and bonding exam papers. The questions are literally the same. So are you telling me that if you know what the questions are, you can't answer them? You know, it's you know, if you already know what's going to be in there and you still can't do it, then I really recommend you not to take level 3 chem, because it's not for you, man. It's not for you. Yeah. I don't get the evaporation pentane. Evaporation pentane. So which one is it? It's over here. Okay, so in what evaporation? What's evaporation? My year 9s had this exam 2 days ago. Evaporation means you're going from liquid to gas. Yeah, so how do you go from liquid to gas? You have to break the intermolecular forces between those particles. So liquid, you can draw, you know, my year 9s can draw what a liquid might look like. What does a gas look like? Something like that. So what has changed? You've broken the intermolecular forces. Therefore, you have absorbed heat to do that. So that's something that you need to worry about. So it's really not that complicated. Okay. Now something like this. This one here. So this is actually a good question. You need to draw this diagram. So this is an exothermic reaction because it's a negative number. So it looks something like that. So the reactants, which are my reactants, is this guys. They go right here. These are my products. They go right here. From here to here, this is negative 3,509 kilojoules per mole. Okay. Reactants, products, and change in enthalpy. Done. Easy. Next one, calculation. So I don't even read the graph. I just look at this. Hey, Amy says hi. Hi, Amy. Justify which alkane produce more energy. Okay, so they're saying that with the head, where is it? Pentane. Okay, so we got two equations. Yeah, Westlake boys. Alright, so we got two equations here. So we can do one at a time. Let's do this one here. Alright, so they're trying to figure out which one produces more heat energy when you burn 125 grams of each fuel. So you got this thing here, and this is what I always do. Yes, it's left. I do have it on 2021. Go search on my YouTube channel. It's here. I've done all the exams from 2018 to 2021. It's all there. Alright, so for this, so can you see for every 2 moles of C6H14, that release 8316 kilojoules. So that means for 1 mole of C6H14, that means is negative, that means is 8316, negative 8316 divided by 2, which is where's my calculator? 8316 divided by 2, and that would be 4158. Okay, so you can see 1 mole of C6H14 give you 4158 kilojoules of energy. I have how many grams? 125 grams. And just remember, in chem, whenever you see grams is useless to us. We want moles. Okay, so we need N equals small m divided by big M. So big M, where the hell is it? Big M? Big M is not this one here, 86. So we can actually figure out how many moles we have, which is going to be 1.45 moles. So 1.45 moles I have, and I know 1 mole is 4158, so that means to go, so the enthalpy change, sorry, the energy, which is Q, is just going to be 1.45 times 4158. And make sure you don't delete numbers from your calculator. Make sure you use the whole number, and this is going to be 604 kilojoules per mole, and this is not rounded to 3 SF, so this should be 6040 kilojoules per mole. Now if I did make a mistake, or negative, if if I did make a mistake, because I'm not looking at the answers, I'm just doing this on my calculator. Okay. Next one. All right, so if you look at this here, same question. So can you see 1 mole of HC5H12, which give us 3509 kilojoules. So I have, again, same thing. I have 125 grams. What's the molar mass? 72. So 125 grams divided by 72, I can figure out how many moles I have. 125 divided by 72, I got 1.74 moles. So 1 mole is 3509. 1.74 moles is just going to be that number times that number. Make sure, again, use everything in your calculator, and that will give us 6092, which is about 6090 kilojoules. Okay, did I say kilojoules per mole here? I think I did. Okay, make sure I don't write kilojoules per mole. Okay, because that's how much energy is being released. Sorry about that. Okay, so this is releasing 6040. This is releasing 6090. So this is the winner. Okay, just want to have a look at the questions. Anyone? No, I don't play Among Us. God of War arrives tomorrow. That's what I'm going to be doing in my spare time. Do we have to round up our values? You need to round your numbers to 3 significant figures. Yes. Level 3 organics hard. If you found level 2 organic hard, you're not gonna do well level 3 organic. I'll just tell you that much. I actually think level 3 is easier. Yeah, 3 SF. Who told you 2 SF? It's always 3 SF. Chemistry has this golden rule of 3 SF rounding. Always round to 3 SF. Yes, Lemon Can, you put, if it's metallic solid, yes. Ionic solids, yes. 3D lattice structure, because that's what they have. But yeah, 3 SF, always 3 SF. We never do 2 SF. I don't know what's happening with it's like you can even see in any of the calculations, there's no to it. It doesn't even say round to what, because it's just given 3 SF. Like you just know it's 3 SF. Ductility, I'll just do that after I do this, right? Like, so I'll just go through. This is the last question on this paper. So this is the perfect example of bond breaking minus bond making. So this is when you have enthalpy, which equals the total of bonds breaking minus bonds making. Okay, bonds breaking minus bonds making. So you just need to break these chemical bonds. So we just need to count. So these ones I need to break, these ones I need to make. But if you know what you're doing, this is the 2016 exam. All right, this one right here. This is a 2016 NCEA exam paper. Okay. Oh, wow, your school recycled the NCEA paper as marks. Hey, someone's a bit slack there. But so what you could do, like I'll just do the long one, then I can show you the short way. Okay. So you can see that here we have 1 CC bond. So look at the bonds breaking. We broke 1 CC bond, which is, we'll do the numbers later. Okay, so there's 1 CC bond, there's 1 CH, 2 CH, 3 CH, 4 CH, 5 CH, 6 CH, 7 CH, 8 CH. Now I'm doing the long way. I'm doing what a typical year 12 would do. All right, but if I were to do this, I wouldn't do it this way. So 8 CH. And then you got 1 CC, 2 CC, so 2 CC bonds. Okay, and then we have an HH right here. So this is my bonds breaking, 1 HH. I think that's all of them. Yes, I highlighted all the ones. All right, let's look at this. On this side, we made 1 CC, 2 CC, 3 CC bonds. So we made 3 CC bonds. And then let's count the CHs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see the benefit of bringing a highlighter to the exam. So that's your bonds breaking minus bonds making. So this is 614. This is I'm blind, 414 times 8. This is 2 times 346. This is 436. Add that up. This is 3 times 346. This is 10 times 414. Add that up. Use this minus that, and you got your answer. Okay. So there you go. And the shorter way is that you can. I'm not sure you can if it's that obvious, but you guys done organic, but you can see that the things that I'm highlighting, like this part, you can see this part is exactly the same. Okay, so you don't actually need to do that part. So if I were to if I were to do it, I'll just do this. I'm breaking CC double bond, CC single bond, and then CH, CH, CH. And this is CH, 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 CC, CC. So there are actually quite a few things you can abbreviate, but you don't need to. I know a lot of you just like to break every single thing and remake every single thing, but that's completely up to you. Okay, and that's the exam. So that's short-term bonding. It's so predictable. It is so difficult not to pass. If you're if you're watching this, that means you want to pass. And if you want to pass, there's no excuse why you shouldn't pass this particular 5 credits external. You just need to put in 5 hours. I reckon 5 to 10 hours, 5 credits. I think that's a bloody good deal. Even if you've been struggling throughout the year, it's a bloody good deal. Take it, learn this topic. This is way more rewarding compared to something like organic. Okay, like, because if you suck at organic, study for 10 hours, I can't even guarantee you to pass, to be honest, if you don't know what you're doing. But with this particular topic, 10 hours, you can do like 3 to 4 exam papers. You will be fine. You will get like 10 points, 12 points. You should be able to secure the chief if you put your mind to it. Okay, so that's the bulk of this standard, and I'll just have a look at your questions now. Because I've done what I wanted to do, so I'm just gonna leave a bit of extra space. I'm just gonna have a look at that now. Yeah, this paper is so easy. Yeah, got it in front of you. You can get the Okay, do you think that type of question will come up? Like, I've not seen this pretty often. Only seen the ones you find. Only see the ones where you find. That's just math. Lemon can. So if you got, for a question like this, where they gave you the bonds and they find you the number, like, it's literally, okay, if you think about this, right, enthalpy equals bonds breaking minus enthalpy of bonds making. So what can they do to give you a bit of a twist? Is that they give you this, let's say give you this, and they give you most of this, but one of those numbers in there is X. So you just need to literally, it's just math. You just rearrange the equation to do what you need to do. It's just mathematics. It's not hard. And I can see a lot of you come from Mr. Infinity Plus One's stream. Surely with a simple algebra equation like that, you guys should have no problem solving. All right, ductility. Thank you for reminding me. So ductility is when you have, how, why do metals remain as a solid if we cut that into wires, hammer that into different shapes, is that the bonding between, the metallic bonding, which is the force of attraction between the delocalized electrons. Let's just say this is delocalized electrons, so what it's doing is, just randomly moving around, doing something, it's going to bond with everything, just going to run around. So what is metallic bonding? Metallic bonding is a force of attraction between this electron with all of these protons when it's moving around. As you can see, I'm just highlighting them as it's traveling around. So what is ductility? So this force of attraction is non-directional. So what it means is that that particular electron is not picky. He can hang out with any one of those protons. All right, he's like a social butterfly. He can mingle with anyone. All right, so it makes no difference to which proton he hangs out with. So right now, if you can imagine, if I grab a saw, chainsaw, or whatever, I start cutting. I cut this part out. Can you see this particular section can still maintain a solid structure because you still have these electrons hanging out in there, and they can still interact with the positive protons, and they can still have the metallic bonding, which keeps the structure intact. Okay, so it doesn't matter what you do to the solid, unless you melt that bloody thing, it will remain, it will always have the metallic bonding between the positive protons and the delocalized electrons, because those delocalized electrons, like I said, they can mingle with any one of those protons. Don't write mingle in it, don't write that in the exam, but you know what I mean. Okay, yeah. Would you recommend not assessing organic? Droppy Junior. So if you're doing year 13 chemistry, do year 12 organic. You will have to do it at some stage. If you're not doing organic level 2, you're not doing level 3 organic. That's 5 credits you're going to miss. That's 4 credits you're going to miss in year 12. That's 5 credits you're going to miss in year 13. And by the time you are year 13, if you do spectroscopy, your school does spectroscopy, which is essentially a lot of organic, you're not going to have a good time. That's what I said to every class of my, especially recently, people in my year 12 classes. If people decide to SNA or not try level 2 organic, I strongly recommend them not to do level 3 chemistry, because it's not personal. It's more about if you struggle with that, if you struggle with it that badly in year 12, you're not going to do that well in year 13. And the sole reason of that is that you guys do the flowchart questions, right? The flowchart questions that you get. If a year 13 version of that, 40%, 20 to 40% of a year 13 flowchart questions come from year 12. So if you can't do year 12, please explain to me how you can do year 13. Like, it would just make no sense to you whatsoever. Okay, no sense to you. You define the 2 types of substance. They say how they're not. Yeah. Resubs are coming back. I'm pretty sure they are, which is typical for our education system, just flip-flopping. Let's not resub. Let us resub. Oh no, let us not resub. I don't even know what's going on. Okay. What school do you teach at? Well, I think it's pretty obvious if you look at my esports stuff. Like all the esports stuff I post is a common school that always shows up. I think it's pretty obvious which school I teach. Is level 3 chem hard? Level 3 chem, like, hands-on hard. I reckon level 3 chem is, personally, if you build the foundation right at year 12, level 3 chem is not that hard. Okay, it's not that huge. Like I always say to my students, level 9, year 9's here, year 10's here, year 11's like here, year 12 is like here, year 13 is like here. It's not that big of a jump. Like this jump from level 1 to level 2 is a huge jump. And then, but if you got the foundation from level 2 to level 3, it's not that big of a jump, because you still, like, say for example in level 3 or chemistry, you still do a polarity. Like if you understand polarity in level 2, you can understand polarity in level 3. If you can do the flowcharts in level 2, you can do the flowcharts in level 3. The only paper that people freak out about in level 3 is either organic or aqueous, which is 3.6. Yeah, I noticed someone said before like 2.6. They said 2.6 is easy, which I fully agree with you, because it has year 11 stuff. But when this thing evolves into 3.6, this is a different beast. This is, but in my opinion, the easiest external in that, if you know what you're doing, minimum amount of writing, can get an E24 in about 35 minutes if you know what you're doing, or calculations. Okay, so, but yeah, if you're doing okay in like, say if you're getting merits in level 2, you should be fine in level 3. Okay. NCEA, yeah, they just, I shall not comment. What do you mean? It's not hidden math. It's literally easy math. You just need to know what the equations to use and apply the equation. It's not that difficult, man. 2.6 is chemical reactivity. It's, yeah, it's not the most exciting external. Yeah. Okay. So have I made videos on level 3 internals? Yes, I have. I have redox. My school, we do redox. We do spectroscopy. Okay. Second in chem. Hey, let's go. Is 2.6 easier than 2.4? It depends on how you see it, mate. It depends. I think 2.4 is the easiest. Well, for people to pass. For me, it's organic. Because it's less writing. I like the less writing ones. Okay. So that's what I thought I would do. Because in the poll that I did, a lot of people wanted videos, like content videos, but then how the heck am I supposed to know which concept you want me to cover? I'm not going to be able to teach you everything that you learn for a whole year in 2 weeks. So I thought about doing this. I just speed run the paper, go through the concepts, and yeah. So no problem. So our stream, our year 12 stream is back in 3 days. So on the 10th, on the what day is it? I lost track again. On the Thursday, it's going to be organic. On the organic on the Thursday, and then Friday, Saturday. So on the Sunday, it's going to be 2.6. Okay. Speed. Yes, yep. All of my VODs are on my YouTube channel. I keep all of my VODs. Yes. Minecraft speed run. Nah. I tried Elden Ring speed run. That was quite intense. God of War comes out tomorrow. Guess who's gonna play that? How do you draw those diagrams where the water molecules attach to polyano? It's easy. Let's say think of any, let's say MgCO3. Let's say, for example. Alright, why the heck do I write that? So MgCO3. What is this? Get out of here. 9164. So MgCO3. So this is made of Mg2 plus and CO3 2 minus. Okay, so this is year 11. 2 plus, 2 minus. If I put this in water, and just remember water, the H's are the positive ends, the O's are the negative ends. So it just comes down to just draw the ions in the middle, like just do that. Just put the positive negative ions in the middle and just face, like say, for example, this is positive. So I want to make sure that my negative ends surround that. So the negative ends are gonna, hey, you're so positive, I want to hang out with you. Opposite charges attract. So you can see how I'm drawing all the O's facing towards the positive charge. On this side, all of the H's are gonna face the negative side. And that's just how you draw the diagram. Nice and easy. No real difficulties here. Okay. Do I draw in 3D lattice? Hell no, I'm not drawing that in the 3D lattice. That's just no point. Okay, no point. Okie dokie, I think we're good. So you should be able to find all of my no, Stacey, I don't need to draw the 3D lattice. You do not need to do that. Okay. So you should be able to find all of my past streams that I've done on the channel. Yeah, it's everything's here. It can be just go through the playlist, just go through the year 12 stuff, and hopefully it'll make more sense. Okay, so if you do have friends that do chem, that are struggling, send them here. Tend to have a bit of everyone from every different school, from top of North Island all the way to Christchurch. So that's next stream is on Thursday. So for the 3.6 SciPad, I personally don't like SciPad. just watch my channel, man. I taught most of 3.6 online because we had lockdown. So you can find 70% of the paper on my YouTube channel on the level 3 concept. So, you know, yeah, SciPads I'm not. ESA study guides are my favorite. You know, I survived my first year of teaching with the ESA study guide. I'll tell you that much. The notes are amazing. Whereas SciPad, the questions are so dumbed down that I feel like I'm being treated like I'm a, you know, very stupid person sometimes. So yeah, but ESA study guides for the notes, and then just grind exam papers if you want to practice. Yeah. Sweet. I'm gonna head out, guys. All the best with your revision. I'll see you guys in 3 days. And then if you, like I said, if you need more help, just drop a question in the comment section. I'll try to attend to your question as quickly as I could. And if you haven't, you can look up there's an NCEA server, like NCEA server on Discord, that quite a few teachers are in. Like, I know Mr. Infinity Plus One is in the server. I'm in the server. It's called NCEA. Let me pull that up. What's that called? It's called NCEA Level 1, 2, 3 Help. How do I invite people? No, I don't. No, I don't have that. It's called NCEA Level 1, 2, and 3 Help. So if you know, tons of people ask questions in there. It's more of a I don't know how to send invites. Wait, how do I send invites without this channel's private? Only element can let's say copy. Here it is. I think there it is. It's all run by students, completely free, and you have student helpers that, you know, answers your questions in all the subjects. It's just absolutely amazing. I really appreciate what some of the students do for the rest of the cohorts. So yeah, sweet ass guys. I'm going to, yeah, that's good. I'm gonna get out of here. I'll see you guys in a few days. All right. In the meantime, study hard. Don't study way too much. You know, don't. Make sure you sleep, and get plenty of hydration. Sleep well. Do some exercise, and I'll see you guys in a few days. All right. Take care.